Okay, what we've got on this video is just that first practice problem for lesson 1-4. So in 1-4, we are dealing with regression models. We're being given a set of data and we're trying to find an equation for a line that fits the data and then also be able to use that line to estimate other points on the graph that maybe we don't have actual data collected for, but we would like to know about. So getting started. First thing we got to do is put this stuff into either Desmos or into a graphing calculator. Just so you know, this video and these first couple that I'm doing, I'm going to be doing this with Desmos since majority of people will probably end up using that anyways. I will, however, go back and do a video, or at least one video, where I do the same problem but with the graphing calculator. So let's get started. Like I said, the first thing we got to do, we need to put this into Desmos. So over here we've got our years, and that would be our X column, and our Y column, the output, is over here. One thing to note, anytime we do years, especially with years, it would be great if we just put 1990 for our X value, 1991. The problem is when we do this, what will happen is the equation for our line is going to be very messy. It's very big numbers. Because if you look at this point, 1,990 in the X, comma, 19,000 in the Y. It's very, very big numbers to deal with. So anytime you have dates, 1995, 1984, 2015, what I recommend you do is make the very first year of your data just be year 0. Just lay it out there. Now, it coincides that it's 1990 and it starts with a 0. But I have already gone and done that for us. So 0, 1, 2, 3, 4 represents 1990 through 94. I've also put in the Y column, and the only thing is, if you remember, I've graphed it. I've turned on the graph for this data set, but I can't see it. So the next thing you do is you hit this little plus magnifying glass. Okay, what that did was it zoomed it to a window that shows us any and all data points in the table. Once we have the data put in, let's actually go back here for a second. The problem says, directions for each following situations, complete the following. Determine an appropriate model is step A. Then explain why you chose it, and C, answer the following question below. So with that said, we're looking at A first, determining the appropriate model. All that means is plot the data and decide, what is my equation, what is my model going to be? So as I look at this, I know it's either going to be quadratic or maybe exponential. So I'm going to look at seeing if this fits in exponential very well. So down here, and again on Schoology, I have these general forms laid out for you. But y1 is about a times b to the x1. That is the model for the exponential regression. Now what you find is r squared is not great. In fact, you can kind of see that if I zoom out, here would be the full equation for the exponential curve. Now, it doesn't really seem to match that too well, does it? In fact, our r squared value is 0.91. So I'm going to turn that off for a minute. The other model, like I said, the quadratic, is here. So you type in y1 is approximately a times x sub 1 squared, bx1, and c. So as you can see, the r squared value, it's already very, very high. I'm going to turn on that graph. If you look, that hits those numbers pretty well, like really well. So with that justification, I'm looking at an r squared value of 0.9991. Yeah, that's good enough for me. So what I'm going to do is I'm going to ask you guys to answer questions A for these types of problems by telling me what kind and what is the equation. So A, the answer is quadratic, and those numbers 304 B, so minus 177.6 x plus 19 So there's our equation. So I would ask that you write that equation down for me in part A. B is asking, explain why that model was chosen. The best explanation for this, and again, I shorthand a lot during videos. Number 1 for time, number 2, because the pen on the screen is kind of hard to write small, so I don't have a lot of room to write. But highest R value is our justification. 0.9991 versus just 0.91. So you could write a little bit more than just highest R value, but the point being, that's how you determine that that's the best. Now, answer the following question, part C. What is your estimate for the amount of waste during the year 2015? Well, so what that's asking us to do here is take this model and, here's 1992.6, here's 1993, 1994. So we have certain data points. What they're asking us to do is estimate what the number would be at the year 2015. So what we need to do is determine, well, what data point is that? And if 1990 is 0, then the year 2015 is data point 25. So what we got to do is we need to zoom out and find data point number 25. So 8, 9, 10, 11, 12, 13, 14. We got to keep going a little ways. And when we get all the way to 25, X25 represents the year 2015. And bingo. It's here somewhere. Give me a second. There we go. So at that point in the year 2015, the estimated tons of solid waste generated is 205,504 tons. So 205, 505. 205. And by the way, the unit symbol for tons, at least for ours, because there are different kinds of tons, is just a capital T. So looking at that, 205,000 tons, then it says, do you believe that this is a realistic value? And my answer is going to be no. And what I'm getting at, so we have 19,000, 20,000, 21, 23,000. To go from a factor of 20,000 tons to 200,000 tons in a matter of 15, 20 years, something like that, 25 years, it just seems a little bit unrealistic because 10 times that amount of garbage being produced, where would it go? How would that work? Clearly, human nature would be to solve the problem and not just let it grow exponentially. That brings us to the point that when we do these problems, we can extrapolate and estimate other data points in the curve, but we really have to be careful how far out we estimate things. So for example, we might be able to estimate, like 1989 or 1988, a few years before it. We can probably even extrapolate data from 1995, 96, 97. We can go a little bit outside of our data collection, but once you get past that too far, you're going to have a hard time really being able to justify your answer. So do be careful with that. The answer being no, too large. Again, I have to shorthand things because of the size of my screen. No, too large of numbers. Or you could also say too far from our original data. This is probably the more acceptable answer. It's too far from the original data. To go that far out from your data is kind of unrealistic to be able to be reliable. So anyways, with all that said, that is question 1 on 1-4. I will probably do at least one more problem. I'll find a good one and do that. Plus, later on, I'll do some of these problems where I use the graphing calculator instead. But there you have it. Thanks for listening.